Welcome, thanks for joining. Grab a notebook, pen or pencil, if you like. Whatever you want to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. Today we have this kind of random problem from 1988. It is a related rates problem, but it's sort of random in that it doesn't have complete representation on an AP exam, but it definitely is an AP caliber problem, and it's certainly a great routine related rates problem. This one involves some trigonometry, which is not always the case, but something you should prepare for in case you're taking the AP exam and you get a question on related rates with a triangle, especially if it's a right triangle. Just be aware that there could be some trigonometry involved. All right, give this problem a shot. You can pause the video if you'd like, and then come back and join me. Now we're going to interpret the problem and understand this diagram that they gave to us. We have a balloon B. I'm assuming this is supposed to be B right up here. And the balloon is rising, makes sense, starting from point C, which is like here on the ground. And there's an observer from point A that is kind of watching the balloon rise. Now the balloon is rising at a constant rate. So they've given us the rate of how fast this balloon is going upwards, which means the Y is getting bigger. And they're also telling us the observer is 100 meters. Yeah, we see that on the diagram. Makes sense. So first we want to figure out the rate of change in x. Where is x? X is this hypotenuse. So we want to figure out the change in the hypotenuse. All right, this all sounds very right triangle, right? Hypotenuse. And we're trying to find the rate of change of that. So we can call that dx dt. And they give us a moment. So when it's at 50 feet, or 50 meters rather, above the ground. In related rates problems, you need to have an equation that literally relates several variables. So in this case, we're going to find a way to relate the thing which is changing, the height of the balloon or the y value. We're going to relate that somehow to the thing we're interested in studying, which is the change in the x, or the hypotenuse. So of course, we're going to use Pythagorean theorem, but you'll notice that this is kind of an easier Pythagorean theorem because the 100 has to remain constant. So we have that 100 squared plus y squared equals x squared. And when we take a derivative of that, I'm not even going to worry about 100 squared is equal to 10,000. It doesn't even matter, because when we take a derivative, we're just going to get 2y dy dx equals 2x, dy dt. Oops, this is happening over time. Equals 2x dx dt. Which is why we can't just leave it as 2x, because we're differentiating these both with time. And they give us a condition. They tell us that y is 50, so this is kind of nice. 2 times 50. We know dy dt is the speed that the rate that the balloon is rising. Speed, rate, pretty much something. That's 3 meters per second. And this is equal to 2 times some x value, which we actually don't know right now at this moment, and then times dx dt. That's the thing that we're looking for. So let's simplify this by dividing the 2 out of both sides. And then we have to investigate, what is this x value? We don't know what x is. We want to get a number there because we need to solve for dx dt. We can't do that unless all the variables have values. So let's go back to this Pythagorean equation and the initial condition, which says y equals 50. That means 100 squared plus 50 squared equals x squared. And now we do have to consider what that is. That's 10,000 plus 2,500. In other words, 12,500 equals x squared. We could just say x is the square root of 12,500. I don't think this is designed to be a calculator problem, so I would just take out a factor of square root 100, aka 10. And you're left with 125. You can even take out a factor of 5, or square root 25, and this would be 50 square root of 5. So you could put it like that if you want. If you want to try to calculate what that is, it's probably about 111 3, 2, 1, 111.1-ish. Anyways. Okay, so we can just divide on both sides by 50 square root of 5. And now that we're big boys and girls in calculus, we don't care if there's a radical in the bottom, it doesn't matter. You could say 3 root 5 over 5 if you've been indoctrinated. But here in the void, follow your heart, live the dream. It's going to come out the exact same in the calculator if you just leave it as 3 over square root of 5. And does it say to indicate units? It doesn't, but we should probably indicate that this is in meters per second. Okay, great. Pretty clear how we're doing this now, right? All right, now we have to find the rate of change in the area. Interesting. So the area of this right triangle, how are we going to represent this area? And again, instant y equals 50. The area of that triangle is just going to be 1/2 base times height. So 1/2 100, which will always be the base as this thing is rising, times the height, which is changing. So the mistake that a lot of students would make is they would plug in y equals 50 right now. That's not what we want. We don't want the area. We want the change in the area. So the area has an equation, 50y, and therefore the derivative, or the rate of change of the area, is 50 times dy dt. Aha. And so that's 50 times 3. We have that given. Remember, this is the part that was given in the problem, constant rate of 3 meters per second. So this is going to be 150. If they wanted us to indicate units, be careful about that. This is meters squared per second. Yeah, it may not look like this is going up by a constant, but the area is increasing by the same amount every time, which is kind of weird, right? That means that these triangles that have very different angles, they're all congruent. It's kind of interesting. Like every second, it goes up by 150 square meters. So that means like the amount of area in this triangle is the same as the amount of area in this triangle, yeah, etc. Okay, that's part B. Part C says find the rate of change of theta. Here we go. This is tricky now. When y equals 50. So again, same initial condition, but we need to now relate two things. This is a related rates problem. First time we had to relate the changing value of y with the x, the hypotenuse. And actually, this does a good demonstration of showing those different hypotenuses, now that I think about it. It's increasing, right? The hypotenuse is increasing by this many meters per second. So these black lines are increasing in length by 3 over root 5 meters every time. Okay, anyways. We had to find an equation that related those two things, which was the Pythagorean theorem. Then on part B, we had to find a way to relate the y value, which is changing, to the area. So we used the area formula. And now we have to relate the y value, which is changing, to theta. So if we use the diagram, then we can come up with a trigonometric expression for the y value, which involves theta. Right? So this is going to be tangent of theta equals y over 100. That's opposite over adjacent. And now we're ready to, if you want to call it 1 over 100 times y, that's fine as well. You can call it 1 over 100 times y. Some people really get tripped up when there's a y over 100. They think like, oh, do I have to do quotient rule, or what's going on here? How do I do that? So let's take a derivative of both sides so that we can get the rate. Remember that the derivative of tangent is secant squared. It's going to be secant squared theta d theta dt equals 1 over 100 simply times 1 dy dt. The derivative of x is just 1, the derivative of y is just 1, but with respect to time, we call it dy dt. Now we're looking for this, which means we have to know, well, we know this, we're given that, we've been using it every single problem, but that means we have to also know this. How do we find out secant squared of theta? Well, if we use the snapshot in time, which tells us that y equals 50, now we're able to use this condition. and we know that this is always 100, we can figure out what secant of theta is. Secant of theta is 1 over cosine. So 1 over cosine squared. Another way to think about it, just using like SOHCAHTOA, it's just going to be like hypotenuse over adjacent squared. So we need this hypotenuse. Remember, we determined that it was 50 root 5. Yeah, because the 10 came out, the 5 came out, and we still have a 5. So this is basically going to be, the hypotenuse squared. Okay, that's easy, which is 12,500 over the adjacent squared, which is 100 squared. That's 10,000. So this is, just cancel some zeros, just go crazy with the zero canceling. And so this is going to be 1.25. Or 5 over 4, if you want, You know what, it kind of works to leave it as 125 over 100, and I'll show you why. You can do it however you want, but I'm just showing you why this is nice. Takes a lot of guesswork out of things. So the zeros, canceling them is obvious. We have d theta dt equals, now dy dt is 3, so this is 3 over 100. We're just going to multiply both sides by 100, cancel them, divide both sides by 3, and we get that 125 over 3 equals d theta dt at that exact moment. And 125 over 3 is in radians, of course, per second. Okay. Well, I hope it was clear how to do related rates after that. There's 3 back-to-back-to-back questions, which I think might be not so typical of the format of an AP question, but who knows? It's very possible that they did this in 1988 when the tests were a little bit different. I could certainly see each of these being a part of a related rates problem, but I didn't expect to see them all in one. Yeah. Anyway, that's enough blab out of me. I'll see you guys next time in the void.